when you take a blood sample of lactate, it's a reflection of the lactate in the blood, not in the muscle. In this case, if you're running at 4 minutes per kilometer and the lactate is 2, and then you exercise at sub-threshold, you do the real good training, and then 2 months later, you're running at 350 minutes per kilometer at lactate 2. Then you will think, all right, I have the same amount of lactate in my blood, but I'm running faster, so I must be a better runner right now. That's not necessarily true, and I'll tell you why. Because
let's start from the basics so the viewer can understand lactate clearly. So from the top, what is lactate and what does it actually represent inside the body?
Yeah, so lactate comes from the cell. And what the cell does is that it takes in glucose, carbohydrates, and then it metabolizes, it burns that glucose in order for you to produce energy. So the cells produce these ATP molecules. And you use that energy for basically movement or living, also
life
eating.
In general.
Life, everything is coupled to energy, right? So that comes from these carbohydrates. But there's a certain point where your body is trying to meet an energy demand. So when you're out running, then you require some energy. And at some point, there's so much requirement of energy that your cells are not able to keep up with that energy demand. So it has to funnel glucose into another pathway, and that produces lactate. So lactate is kind of like a partially burned carbohydrate. So it still has energy in it. It's just not completely burned to water in this case, which is the normal pathway.
So lactate is produced in the body because the energy demand of the body is higher at a non-resting state. So the carbohydrates or the glucose or glycogen goes into a different pathway, and a so-called byproduct of that incomplete glucose metabolism is lactate.
Yeah, I think that's one way to frame it. That is correct. But you also produce lactate at rest. So the body is always trying to disperse energies into different pathways. So not just to maximize one pathway, but in this case, you have 2 pathways. One, the glucose gets fully oxidized to water. That's through oxidative phosphorylation process. And then you have cellular fermentation, or I call it the kombucha pathway. So you're fermenting. In this case, you produce lactate. But you have to understand that these 2 pathways, they always one. It's not just choosing one pathway or the others. Both of the pathway runs. So
simultaneously.
They run simultaneously, always. Also at rest. They just run a bit more when you're exercising, because at rest, you still have an energy demand. Because if you didn't have energy demand, then you'll not be living, right?
Correct. Yeah.
You're done. So it's just that the body wants to use both these highways, right? If you have a highway that's like really fast, produces a lot of energy, but it's like slightly clogged, there's a bit traffic jam, then you might as well use the other highway. It's there, so you use them simultaneously.
So lactate is always produced regardless of whether you're at rest or at work. When I say at work, as in exercising, racing, training, and it's a result of carbohydrate and glycogen metabolism, an incomplete byproduct of glycogen metabolism, right?
Yes. So the whole premises of a cell is to take it energy, oxidize it, which basically means burn it, and then produce energy. And in this case, lactate is an incomplete oxidation. So it means that the sugar, the carbohydrate, the glucose has not been burned completely yet.
As we pivot into thinking about lactate as a data point for improving performance, let's clean up the language a little bit, because I think there's a bit of confusion there. So when we talk about lactate thresholds, Based on my understanding, there are actually two lactate thresholds, LT1 and LT2, right? Lactate threshold and 1 and lactate threshold 2. How would you define each of this in simple but accurate terms? Peter and I talked about why a single lactate data point means almost nothing. What matters is tracking the right metrics over time to see what is actually changing. The same principle applies to body composition. If you're still using the scale to track fat loss, you're getting one number. It does not tell you whether the weight is coming from fat or muscle. As a masters athlete, that distinction matters because losing fat is awesome, but losing muscle affects your power output, your running economy, your glucose regulation, and your ability to sustain intensity over time. That's where the Hume body part becomes very useful. Instead of one number, it shows you how your muscle mass and body fat are trending over time, broken down by region. It even separates subcutaneous fat from visceral fat, which matters most for metabolic health. It gives you clinic level accuracy from home. And because it tracks over time, you're building a data set that's meaningful. Use code ENDURANCELAB for 20% off. It stacks with Hume's current sale for up to 50% total savings. Valid for 7 days. And for US listeners, it's HSA and FSA eligible, so your insurance may cover it. Thanks to Hume Health for sponsoring this episode. LT1 and LT2, right? Lactate threshold and 1 and lactate threshold 2. How would you define each of this in simple but accurate terms?
Yeah, sure. So this is mainly from science because we want to put labels on everything. Essentially, when you do a lactate test, that's going to be a ramp-on protocol. For example, you're on a treadmill, you run, let's say, 2,000 meters, 1,600 meters, and then you measure lactate, and after that, you increase the pace on the treadmill a bit more and you repeat the experiment. If you do it and then plot these lactate values on a chart by having millimolar concentration of lactate in blood on the y-axis, and then you have speed of the treadmill on the x-axis, then you get this kind of, I'll always call it like an infamous curve of increasing steadily, and then at some point, at some pace, it's going to increase exponentially. What you see in the beginning of the experiment, when you're just jogging along, then there's not a lot of increase in lactate. It's that baseline, but this baseline also fluctuates. But let's say in this case, it's like 1 millimolar.
Okay.
So as you increase the pace, then it's still at 1 millimolar, and then at some point, it suddenly goes to 1.5. At that point, it goes from baseline to start increasing. That's what we call LT1.
Okay.
After this, you increase the pace further on, and then you get an increase in lactate. It becomes 1.7, 1.8, 2.5, and then suddenly, at some point, it increases exponentially. So it goes from 2.5 to 4.5. At that inflection point is what we call LT2, lactate threshold 2.
Okay.
So scientists kind of said, okay, so this point LT2 is around 4 millimolar of lactate. This creates an easy way for scientists to have a consensus about, okay, we can do experiments because now we have a definition of lactate thresholds. But in reality, it's more difficult.
Okay. You mentioned LT2 as 4 millimolars per liter, and you also mentioned that LT1 is at 1.5. But we also hear quite often other scientists or in literature talking about LT1 or zone 2 being 2 millimolars per liter. How does that relate to what you're saying about 1.5? In the eyes of different scientists, do they look at LT1 at different levels of lactate between 1.5 and 2 millimolars per liter?
Yeah, I think there's a different in definition.
Okay.
And there's a different in backgrounds. So it depends on where you come from. In this case, an LT is a lactate threshold. So that's kind of like one point in the chart. While if you're looking at zones, then you're looking at an interval, like it's some kind of range in this chart. And that's why there's some discrepancy and people get confused about it. And then if you come from biochemistry, then you probably call LT1 for aerobic threshold and LT2 for anaerobic threshold. So all these terms, they also depend on who is the receiver of this message and like what kind of scientific background I'm coming from. I would argue that it doesn't. I mean, it doesn't really matter what you call them and how you place them on this curve. The thing that really matters is that how would you use this information to improve your performance? Because you just have to remember, in the end, all these terms, if they confuse you, just go back to basic. Why I'm doing this training? Like, what is this session for? I'm trying to run easy. I'm trying to improve my lactate threshold, or I'm trying to improve my VO2 max. This is just going back to basic physiology. Like, what is the end goal of what you're trying to do, rather than going to extreme science part of it. Because I'm a scientist. I love science. I've done my PhD in sports medicine. But if you had to ask me, who would I want to be trained at? Like, who wants to train me? The world's best scientist or the world's best coach? My answer would probably be the world's best coach, because that person knows reality, and reality is more like an art than it is science.
Now let's talk a bit about the science part. Generally, lactate for most people is measured in a lab setting. Is there a difference between measuring it in the lab setting and assuming someone is out in the field, like in real world, whether in training or in a race? Does it actually differ, and do different testing protocols differ? There is an interval period between each probe, each test. Does a change in that interval period, or does a change between the intervals of heart rate affect the actual results based on the testing protocol?
Yes, I think that's a really good question. And it goes into the exact difference between science and the real world. Because science, and when you're in the lab, you have to make a protocol that's very controlled. So you're on a treadmill, it's probably been calibrated. There's a medical staff right beside you taking all the samples. You only have to concentrate about running, right? It's probably also room temperature, or maybe a bit fan running in the background, all these things. That's completely different when you're running on the track and doing these things. So on the track, there might be wind gusts. The surface is different, and the temperature is also different. So all these things is something you have to take into account. Unless you're doing races on treadmills, then I prefer to do this test outside. Okay. Because it depends on the protocol you're using. Again, we have to understand that lactate is this pathway of cellular fragmentation, this kombucha pathway that essentially tells us how stressed out are the cells. So in this case, you can stress the cell by two ways. You can cut the energy availability to the cell. In this case, it's oxygen. Or you can increase the energy demand on the cell, which is basically running faster.
Okay.
Right?
Okay.
There's a special situation by cutting energy availability to the cell, and that is cutting carbohydrates to the cell.
So does that mean in a glycogen depleted state?
Yeah, so it means in a glycogen depleted state, what happens is that you don't have a lot of glucose in the system. And you can test it. Like, you can wake up in the morning, you can run 35K. That's called a depletion run without any breakfast. And then later on, you do your 10 times 1 kilometers on the track, and then you just measure lactate. And even though you're exercising, you're like pushing yourself really hard, it wasn't possible for me to get lactate above 3 because there was no glucose present. Okay. So because there's no glucose present, then the two pathways we talked about are kind of downregulated. Like, nothing's coming through, right? Yeah. So in this case, there's a decoupling between the intensity and then actually what you measure on lactate measures.
So the availability of glycogen has an effect on your lactate reading during that workout.
Yes, and that's why I'm always against lactate test. I think they're nice, but eventually a test is a snapshot in time, and that lactate reading, those results you get from a lactate test, they are based on your current form that day, what you've been eating, what is the temperature, how was the treadmill calibrated, how was the lactate test taken, because that's something you have to take into account. Like you're taking a finger prick, and then you have to wipe out the first like blood problem, and then you take your sample. I've experienced a lot of errors in this process of taking lactate samples. If you just touch the tip of your lactate strip on your finger, then it's contaminated. You get a higher reading. All these kinds of things have to take into account. And
I've noticed that on myself as well. It's a very dirty reading. Sometimes I have to take 2-3 times just to get an average.
Yeah, definitely. If you've done a few thousand tests, then you get this golden badge. Like now you know how to make lactate testing. I can do it now. It's like it's going to take me 10 seconds.
Okay,
it's through a lot of experience. You're right.
No,
and it's kind of
I haven't got to 1,000 yet, but I've done some. I mean, I've got my lactate meter right over here, and I do prick myself every now and then, but not close to the amount that you have done.
Oh, well, I recognize. Is that the Lactate Pro 2?
Yes.
The blue one.
Open it up.
It's the casing. Yeah. So
it's the Pro 2.
That's a good one. Yeah.
Yeah, but it's true. I mean, sometimes when I'm trying to test for like 2 millimolars and I know my intensity is about there, and then I do the first prick and it says like 4 or 5, and like that's not possible. And then I clean the blood off and I squeeze out a bit more and I test it again, and it comes to somewhere around 2. And I'm like, okay, now we are in the range of what it kind of should be.
Sometimes you can either, you can even have a really good meal before running. And if you ingested a lot of carbohydrates, well, guess what? Your lactate is also going to be high in this case.
Okay.
And that's kind of independent on whether you are working out or not. Like you can sit on the sofa, you can try it, eat a loaf of bread. Okay, maybe not that much. Okay. Too much. Like just eat a couple of slices of bread and then the measure before and after just to see the shift in baseline. It's kind of funny. And again, it tells you, okay, so now energy availability is no longer the bottleneck. So the cell has to capture all that glucose, and once it does, then it has to go somewhere, right?
Okay, that's super interesting.
You're putting a lot of glucose through both pathways.
I'm going to put that on hold for a while because I definitely want to go a bit more into fueling and its relation to lactate a bit later. But let's clear a few more terminologies as well so people really understand what we're talking about. So earlier you talked about LT2 being about 4 millimolars of lactate per liter. And there is this term as well called MLSS, right? Maximal Lactate Steady State. How does that relate to LT2? Is it the same or is it different in terms of intensity of output?
It's different, and this also was something that was experienced in the field because researchers thought they figured out by saying, okay, so it's 4 millimolar, and if you're above it, then you're at this exponential curve, like it's unsustainable lactate levels. But then when we went into the field, you saw people who were at 6, 7, maybe even 8 millimolars of lactate, but they could hold the intensity. So you were above LT2, but it wasn't increasing exponentially. And that was kind of strange. So they came up with a new concept, and this is the MAXLATE, the maximum lactate steady state. It basically tells you that there is a certain steady state of lactate you can hold that doesn't make lactate increase exponentially. And it can be way above 4 milliliters of lactate.
That explains something that I've been wondering about for a long time. So let me give you my personal example. And the reason why I'm wondering about this is because I'm training for a sub 3-hour marathon that's going to be in 6 weeks' time. All right. And to run a sub 3 marathon, I need to be running just under 4 minutes, 15 seconds per kilometer. That's my marathon pace. And at that pace, my heart rate is around 170 beats per minute. I know it's pretty high for a 48-year-old dude. And when I test my lactate on a treadmill at that pace and at that heart rate, it's about 6 millimolars per liter, which clearly, like what you just said, it's above LT2, right? It's above 4 millimolars per liter. But last autumn, I ran a 3:05 marathon. I was targeting a 3 hour as well, but I didn't make it by 5 minutes. And my average heart rate across that 3 hours, 5 minutes was 169 beats per minute. So that heart rate data with pace, and when I test it on a treadmill, tells me that it's 6 millimoles per liter. And what I couldn't figure out for all this time is how is it possible that I am running for over 3 hours at a lactate volume, so to speak, above threshold 2. So what you just explained, that MLSS, maximal lactate steady state, can be above 4 millimolars per liter, and for different athletes is different. That's why I could sustain 3 hours at that intensity. Is that correct?
That's correct. I get.
Okay.
It shouldn't be sustainable, but it is. And that's probably true for even shorter distances. People running miles, they can sustain a really high max mass, and it's basically genetics involved, but it's also some kind of training. We're not quite sure what kind of training there's needed right now. I think Steve Magnus has talked about how to increase max mass, but we can only speculate. Definitely, I don't have the recipe for it.
Okay, but it's possible. Even though physiologically and scientifically speaking it's not possible, but in the field it's possible.
Yeah, I think scientifically we can do some experiments to verify how max mass could be working by doing some infusion of radio isotopes of lactate. One way we think it's being introduced in the body with this max mass is that you produce a lot of lactate, but then it's also cleared very fast. You have to understand lactate was this incomplete oxidation of glucose. So when it gets transported in the body, then the liver clears it out. The kidney also clears it out. So what the liver essentially does is glyconeogenesis. So it takes in lactate and then it produces glucose back again.
Okay.
In this situation, you can have a steady state in blood at 6 to 7 millimolars of lactate, way above LT2.
Wow. Okay. Is there also a mental side to that ability? Because my hypothesis from my own data was when you're at a race, you are mentally ready to give it more than 100% of your effort. And then with the crowds and with your goal in mind, you push to the absolute maximum of what you're able to, compared to when you're doing it on a hard training session. That mental side of it pushes me to maintain that MLSS beyond LT2.
Definitely the mental side has some meaning to it, because in the end, that's probably one of the most important things on race day is the mental side. It can also be that because you're running a marathon at, let's say, progressive speed, like you're running negative split, they can also help you bring up that max mass to way above LT2, because you're slowly warming up the body. I mean, a marathon, I ran Valencia Marathon last year in 2:39, so the weather was too hot for a PR. But for my small experience of marathon running is that the first 35 kilometers of a marathon is just transportation. and just try to make it on the last 5-7K. And because you usually run a marathon progressively, then you kind of warm up all the systems, like the heart, the lungs, the liver, all these things, all these enzymes, they slowly kind of wake up. Maybe that's why you have a easier time holding a lactate level above LT2.
Let's pivot a bit and talk about lactate as a marker for training. And I struggle with this, and I think people that start to test their lactate, well, whether it's by themselves or in the lab, they would also start to struggle with it, because how do they make sense of that measurement? So the first question is, what factors can actually distort a lactate reading, whether it's sleep, stress? I know we talk about carbs, but hydration, caffeine, what actually can change the lactate reading of that point in time?
I would probably say everything. Just to make,
Okay, if it's everything, so how does someone make sense of
yeah,
that lactate reading?
just to make everything complicated, because you're working within the biological limits, right? So
Okay.
I know for myself, in the morning, my lactate levels are really high. So I have to be super careful in the morning sessions. Uh, I will run longer repetitions in the morning, like let's say 4 minute reps, and those will be around 4 minutes per kilometer.
Okay.
And then in the afternoon, I will run maybe 85 seconds repetitions, so they're shorter, but they will be around, let's say, 330.
Okay.
So that's 30 seconds per kilometer difference between those two. And in the morning at 4 minutes per kilometer, my lactate is around 2.0. So that's
4 minutes per kilometer.
that's really slow. I run a half marathon in 1:14, so I can't go any faster in the morning. That's just how it is. I just have to accept it. And it might be because when you're waking up in the morning, cortisol is spiking at around 6 a.m. just before you wake up. Now I have kids, so my cortisol is always spiking, but it's probably high around 5. You wake up, cortisol is a stress hormone, but it's also there to mobilize glucose into the bloodstream. It's like telling your body, you have to wake up now. Because I'm exercising super early, it might bring additional stress to the body. And that's why I have to be careful. And another person might run even faster. It's really about feeling, how are you from day to day, session to session, and then assigning kind of like a red, yellow, and green light to those days, so you know when can you push a bit harder, and that's super difficult. It's almost like you need the experience, or you need some kind of continuous measurement of your body to know these kind of signals.
So if someone is just going to go out and get a lab test, I'm guessing based on what you just said, it's going to be very difficult for them to use it to guide their training decisions.
Yes, because it needs to be the opposite way. You don't get a lactate test to train after the lactate test. The lactate test needs to support you. So that's why it's a bit difficult. So it requires a lot of training samples over a certain period of time, and then be very structured, very strategic about how you plan your sessions, so you understand what's going on. Because the lab test, whatever test you're taking, is just at one point in time, and you need that to help guide how you feel. You don't use that point in time to train after it. And I think that's how people sometimes get burned out or maybe injured and all these things, because they think, okay, I did a lab test, my LT2 is 4 minutes per kilometer, so if I'm not touching 4 minutes per kilometer, then I should be fine. I'm sub-threshold. And then they go out and exercise, and after a few weeks, then they get bored and they think, okay, I need to increase a bit more because my fitness has increased. It doesn't work that way. I mean, it's from day to day. Now, I gave you an example of 4 minutes per kilometer in the morning, or a morning session. That could be a good day. On a bad day, it's 4:10. And so the whole exercise is really not about lactate. It's about, are you able to read your body signals and then take the correct countermeasures in order to get the adaptation you want out of that specific day? Are you able to actually go down in pace? Can you eat that ego? Can you kill that ego of not going too fast to capture the correct adaptation with the minimum amount of effort? This is how you produce lactate. You shouldn't say, okay, I measured 2.0 on 4 minutes per kilometer, so I can run exactly to 2.0. There's no reason to err on the unsafe side. You don't have to dance around the edge. Go down to 1.5. That's okay too. Because the risk of overreaching, it's so high, the diminishing returns are super real in this case. Like, do you want to risk it all for just 1% more, or do you want to just back off a bit and get 80-90% of all the benefits?
Mm-hmm. Yeah, exactly. So just so I understand what you just said, taking a lactate reading as a snapshot in time shouldn't guide your training decisions, but rather it should be a reflection of the training that you have done previously.
Yeah, I think so. So, okay, I think lactate tests definitely have their role in training, and I think lab test has as well. But as you said, it's a reflection of your current status, like for that day, for that specific protocol. It doesn't necessarily mean that this is how you should structure your training program.
Would it be fair to say that with the introduction of continuous lactate meters, that would change? So if we are continuously reading our lactate like we would our heart rate, we could actually use that to guide our training decisions better.
I believe so. I think so. Lactate is just one measurement you can do, and in the future, it's going to be lactate, and then it's going to be more things. Because basically, what you want to measure is actually not lactate. We have to come back to what makes sense for the athlete, and that's training intensity. That's essentially the currency of the cell is ATP or electrons in this case. It's electron flow. So you're trying to measure how hard is this cell actually working, because for all life to develop, to be stronger, you kind of need to push it a bit, but not too much. You could exercise exactly to 2.0, but do you really want to go there? Like, it's so close. This errorless side, staying 1.5, like it's going to take longer. And then you realize, wow, at one day I was 1.5 at this pace, let's say 410. And then the other day I was at 1.8 at 410. So you have a buffer, you have a range of things for the days to go on. Instead of being always at 2.0, 3.0, now then there's no buffer. Like, you step forward and you burned, you cooked.
All right. So earlier you talked about the lactate curve, right? That is going to start flat and then it's going to hockey stick up. And when we think about improving performance or improving our lactate threshold, we often hear about shifting that curve to the right. Why are we trying to shift the curve to the right?
Normally, if you shift the curve to the right and you have pace on the x-axis, it means you can now increase the pace before you get to that hockey stick. This is where it gets a bit tricky, because increasing the lactate curve to the right doesn't necessarily makes you a better runner.
Okay.
Because there's many ways to increase the curve to the right. Remember, when you take a blood sample of lactate, it's a reflection of the lactate in the blood, not in the muscle. In this case, if you're running at 4 minutes per kilometer and the lactate is 2, and then you exercise at sub-threshold, you do the real good training, and then 2 months later, you're running at 350 minutes per kilometer at lactate 2. Then you will think, all right, I have the same amount of lactate in my blood, but I'm running faster. So I must be a better runner right now. That's not necessarily true. And I'll tell you why. Because the lactate that's being produced in the muscle, now we're in the muscle.
Okay.
That lactate can also decrease. If that decreases, and you have the same clearance in the blood, then the lactate in the blood also decreases, right?
Yes, yes,
so
exactly.
Basically what I'm saying is that if you are able to lower your threshold, this is what's called lowering threshold, from 4 minutes per kilometer to 350, you might think, okay, I'm a better runner right now. But if you decrease the threshold and then compromising on your muscle strength, then it means that you have now become a weaker runner. So you can actually change the inflection point of the lactate curve. So the lactate curve can also change in itself, because when you're decreasing the threshold in pace, or you're running 400 or 350 on the same test a few months later, then you assume the lactate curve is still the same. But the lactate curve can also change in itself.
Okay, so moving the lactate curve to the right might look good on paper, but it does not translate always to you becoming a better runner in the real world.
And there are some good books about it by a previous coach called Jan Olbrich. He did a lot of lactate tests on swimmers. So there's two opposing forces called aerobic capacity and anaerobic capacity.
Okay.
So they're kind of like pulling the strings on this lactate curve. So
is that book Science of Performance or Science of Winning?
Yeah, the Science of Winning.
Okay, the Science of Winning. Yeah, okay. I know of that book, yeah.
It can get really technical, but just think of it like this. You do your lactate test, and then you do a max running test, 400 meters. The fastest you can run it out, so 400 meters, let's say 60 seconds. So the lactate curve tells you your LT2 is around, let's say, 4 minutes per kilometer. And then you're running 70 seconds on the 400 meters. But then 1 month later, you're now decrease your lactate threshold to, let's say, 350 pace. Mm-hmm. But your 400 meters time has now increased to 80 seconds.
You're becoming slower.
That is absolutely possible because you decrease the strength of your muscle and then you increased some duration in your muscle. But then this means that if you're running for your specific event, then this can absolutely wreck your event, especially if you're running shorter events. In this case, you have to be super careful because a lot of these middle distances or short distances, they are won in the last 400 meters.
If improving lactate doesn't relate to performance, how would someone use that as a practical tool in their training toolbox?
I think the only way to use it properly is to use it over long term and then do races.
Okay, so does that mean like you track the data over a period of time and see how it trends?
Yes. I think it only makes sense to track lactate over time, have a decent amount of data points, and then you have to remember the best way to measure performance is performance itself. Mm-hmm. So go out, do a race. I mean, if you're able to run your marathon under 3 minutes per kilometer, then that's your performance. Use that lactate point to guide your training and the races to kind of get a real world estimate of your current form.
Okay, so a once in a month or once in 6 months lactate test, it's not possible to guide your training. But if you continuously test your lactate, I'm extrapolating based on what you said, that when you have that continuous data of lactate testing, you can see how you are trending in relation, your performance in relation to your lactate readings. And that's how you use it to guide your training.
Yeah, I think it's the same as heart rate. I think a good way to look at it is like lactate is just another heart rate. It's heart rate 2.0. So it's the cell's heart rate. And at a given point, this is just a snapshot in time. So kind of need to establish a big data set in order to get some kind of meaningful data out of it, and then do frequent races. That's why many of these things are kind of like N=1 experiment.
If someone has constant lactate data, what does it reveal that heart rate, pace, and power does not reveal to us? Why is it a useful measurement?
I think it's useful because it's kind of like everything brought together. Like the pacing, the heart rate is all there because the cells are stressed out. Again, we have to know why we're doing these things. Like we want to measure training intensity. Like we want to get it as precise as possible. And in this case, lactate is just really proxy to the intensity. And the intensity, again, is correlated to the energy demand of the cell. This is also why heart rate is kind of like a lagging indicator, because heart rate is essentially because the cells need more energy input, in this case oxygen, and then wash out CO2, bring in glucose, all these things. But they're only relevant if your cells scream for it. Like they will literally tell your body, okay, pH is dropping right now. We're exercising too hard. We can't keep up with demand. Tell the heart to pump harder.
Okay, let's circle back to fueling. We talked a bit about carbohydrate ingestion affecting lactate reading. So, there's a big conversation between how an athlete fuels these days, right? Some are in the high carb camp, some are in the high fat, low carb camp. And considering the lactate is produced when the rate of glycolysis exceeds the rate of mitochondrial oxidation, correct? So that means lactate is a byproduct of glucose when it's not completely metabolized. So talk to me about the different fueling strategies and how it actually influences lactate production.
The two extremes is high carb, low fat, and then high fat, low carb, right? So yeah. I think those two are kind of in their base camps, and I think it was very popular a few years back on training with this high fat, low carb regime. I'm heavily against it, but I know some other people are not, and it's just really it's really about what you want out of the training in this case. So there's no wrong or right. So I'm very political right now, but it's true. If you want to perform at your best, you need carbohydrates, and your body will crave carbohydrates. So if you're doing double thresholds, following the Norwegian model, exercising at the highest level, and you're doing high fat, low carb, then your lactate will probably be low. Like you can push your body really hard and not spike lactate above 3 or 4 in this case. Okay. But you're going to feel miserable, and the training intensity is going to confuse you because you're exercising really hard, and then you're measuring lactate, but it's only 2. So you think, wow, I'm super fit, so I'm even harder. But again, there's nothing to produce lactate off because you deprive the body of the and carbohydrates. So, of course, you're not going to measure a high level of lactate in this case. But that doesn't mean that you become a better runner from it.
Correct. Yeah.
So you become a better runner by stimulating the enzymes that are directly involved with energy production. So carbohydrates funnel through glycolysis, super metabolized to water or lactate. You need to push on both of those pathways.
Okay.
Because remember, then I talked with this electron flux, but it's true. Like, you need to maximize electron flux through your cell, and then when the lactate gets in the bloodstream or electrolytes accumulates, you need to clear it really fast. So that's a very, very high flux through your body of energy. That's how you increase the performance.
Okay,
and if you're running on high fat, yes, there's a lot of energy in fat, but it's just super hard for your body to break it down. And still, when you're high fat, your body will still need carbohydrates. And this is because in the biochemical pathway, you need to have pyruvate that gets metabolized to oxaloacetate, and then it reacts with fat. So you need carbohydrates in all points of time. Like it's impossible to live on a 100% fat diet, because then your body will just strip your proteins from the muscle and then produce carbohydrates.
Correct. What's the term for that? Gluconeogenesis?
No, I think that's just breakdown of proteins.
Okay.
Gluconeogenesis is essentially what runs in the liver. But you're right. It breaks down.
Breaks down protein through the liver, and then the liver converts it into glucose, and it gets excreted in the bloodstream for somebody that's on a full ketogenic diet, right? So it's the breakdown.
So glycogenesis is mainly for specific organs. In this case, the liver or the kidneys, because they have this glucose 6-phosphatase. So they are actually able to take out 1-phosphate from glucose. But when your body is catabolizing, is eating itself to get carbohydrates, some of those amino acids, they just go directly into the muscle cell, and then they come in as intermediates in the glycolysis. So that's outside of gluconeogenesis, like it's outside the liver. It's just run through the glycolysis system. It goes downstream.
All right. Okay. So with high carb, you will see a higher lactate reading, and with high fat or with low carbs, you will generally see a lower lactate reading when you are training. So with that in mind, can lactate data actually help to guide fueling strategies in training and racing?
Yeah, so if you're on high carb, low fat, then yes, you might get a higher lactate reading, but I will tell it in a different way that you get the right lactate reading in this case because you have energy availability in the cell.
Okay.
So it reflects the current stress on the cell because the bottleneck is no longer energy availability. But in a high fat diet, then that's the bottleneck is energy availability. So I would probably do sparingly. I'm not a coach, but I just know from science and also from a lot of other athletes that restricting carbohydrates before a training session is generally not a good idea, even though it sounds really great, because training itself is already a major stress on the body. So there's no reason to overstress it. Like,
to add another layer of stress. Yeah, that's true. That's true. Man, I mean, there are so many views on that at the moment. And I've already had conversations with people on both sides of the spectrum. And I see the trade-offs on both sides, and I see the benefits of both sides. And like you said just now, it really depends on the goal that you're trying to achieve. And I think the same stance that, if you are trying to maximize performance, you definitely want to be consuming carbohydrates. But if your goal is maybe to lose that 20 extra pounds of fat and you're using aerobic training as a tool, you might use the high fat, low carb approach periodically to help you achieve that goal. But when performance comes into play, there is no question with carbohydrates. Because these days, elites are pushing 120, 150 grams of carbs, and they are smashing records with that kind of fueling strategies. So it is clear in the elite world that strategy works.
Yeah. I also think everything is moderation. And I think it depends on what your goals are. But there's also a lot of athletes that just keeps fueling carbohydrates, and they're all fueling themselves. So they kind of get this in this pre-diabetic state. Like they're really good shape, but then the blood glucose is super high, or the HbA1c is super high too. So, and they didn't know this before they went to the doctor. So everything needs to be in kind of this moderation, and that makes things much more difficult because where do you draw the line? But in reality, if something sounds too extreme, it's probably not a good idea. I mean, even for a person who wants to lose weight, remember how one gram of fat is 9 kilocalories, or so it's a lot.
Nearly double, more than double of.
But well, in the end, if it keeps you full without overeating, then that's probably your strategy.
Yeah.
But again, I think it matters more of what you eat instead of counting carbohydrates, proteins, or fat, because in the end, it doesn't really make sense if you think about it. Like, because you're not eating just fat, or you're not just eating carbohydrates. Like you eat meals, right?
Food. Yeah, you're eating meals. Yeah, exactly.
Into your mouth, and then you're getting food in that way. So that's why generally I tend not to have energy drinks, because that's just like the fastest acting glucose you can ever introduce into the system. Like it just goes straight into the bloodstream and into the cells.
But do you think it has its place when you're racing or when you're doing a really hard session?
Absolutely.
Okay.
Especially during races. I mean, I also take energy drink during marathon, and in really tough training environments.
But I think the problem comes when you're taking it at rest.
Yeah, and also you have to be strategic about it. So when are you exercising, and when do you need the energy? So it's about energy availability. So for example, in my case, I exercise in the morning and then after work. So I run to work and then back home. In this case, I'm front loading myself with carbohydrates. So And it's kind of like simple carbohydrates that will make another doctor go, oh, this doesn't look healthy. Like it's white bread. It's very simple. But it's just to get not to get my stomach upset. So I use a lot of meals that contains high level of carbohydrates in the morning, and then in the afternoon, because I'm done with exercise, like you need to rest and digest. So there's a high micronutrients of proteins and fats in
got it.
dinners.
Like carbohydrate periodization, so to speak.
Yeah,
fueling for the effort.
Like intraday, but if you really, it sounds kind of difficult, but sometimes if you just listen to what the body craves, then it's going to give you the signal that okay, you probably need to see some carbs right now or protein or fat.
Yeah. Exactly. Okay, let's pivot and talk about now moving into the future. So a few years ago, CGMs, continuous glucose meters, have come onto the market, and a lot of people have tried it and used it. I'm one of those. And now we are starting to see CLMs, right? Continuous lactate meters starting to come onto the market. You are building Athyx. Did I pronounce it correctly? Athyx, Athyx. You're a co-founder, and the idea of that is around making continuous lactate measurements more accessible to an athlete. And your first product is called the Flux I, which was launched 3 weeks ago.
Yes, the Flux One was launched two weeks ago. Yeah.
Okay, two weeks ago, and it's now shipping worldwide.
Yes, correctly. Yeah, we're shipping everywhere.
Okay. What problem are you trying to solve with Athyx and your continuous lactate meters? Considering the fact that you're saying that even if someone works towards shifting the lactate curve to the right, it doesn't mean that they're becoming a better runner, and that there are so many factors that affect a lactate reading. So with the premise of Athyx, what problem are you trying to solve for the athlete?
Athyx is more than just wearables. We are a software first company. Okay, so there's all these measurements you can take. Like lactate was just one of them. And we're making a lactate sensor because we think that's like the closest to truth of training intensity you can get. That's lactate.
Okay.
That's one thing. And the other thing is that we are creating this ecosystem. Like we have an app, we have the website with a lot of learning, educational articles, and get people to understand how to interpret the signals from the body and become better athletes. So we are performance first. So we're trying to solve the problem by giving athletes, users, customers a way to understand their body better so they can take the right countermeasures, take the right choice in exercise. And this is what we call the alpha, like this asymmetrical risk. Like how can you get the most benefit with the least amount of effort?
Lactate measures glycogen that has not been fully oxidized, right? And we also know that between an elite endurance athlete and someone that is pre-diabetic or someone that has metabolic dysfunction or inflexibility, for someone that has metabolic inflexibility, when they start very light exercise, they're probably using a much larger percentage of carbohydrates or glycogen than an athlete that is fat adapted, a very well trained elite athlete. Could continuous lactate meters tell someone their metabolic flexibility based on that reading? Yeah,
I think metabolic flexibility is kind of one of those terms that there's not a clear definition of it. But it means, like you said, in this case, that you are incapable of flexing between carbohydrates and fats and proteins. Like you're just bounded by carbohydrates in this case. And again, basically, it means you're out of shape.
So yeah, exactly. Yeah,
you just use a lot of carbohydrates even at rest. And yes, in this case, there's a very good correlation between the metabolic flexibility and the lactate measurements you're getting. Because if you're reading 3.0 millimolars of lactate when you're just walking, then guess what? Walking is your exercise.
Yeah, that means, it can show that you're metabolically inflexible, right?
Yes. So it it just tells you that the enzymes in your body are just very one-sided. They're just trying to maximize glucose oxidation in this case. So to enable to become more metabolic flexible, you have to stimulate the other enzymes as well. The fat oxidation, protein breakdown, all these things, all these plethora of enzymes, they need to be stimulated. But it can only be stimulated if you just give them just enough to let them know that they are not sufficient to maintain your current status or your current performance. Then they improve themselves. You get this mitochondrial biogenesis. Mm-hmm. You get this kind of adaptations that allows you to become more flexible. Because if you just have a small pool of mitochondria, then the easiest way to get energy is just to go through glycolysis and just completely oxidize carbohydrates.
So apart from an athlete using Athyx to measure their lactate for performance, would someone just using it to define their metabolic health or to tell them where they stand in their metabolic health across the spectrum, would that be a second use case of a continuous lactate meter?
I guess you could use it to get some kind of metabolic insight.
Okay.
I mean, we don't restrict it to any special use case because it's essentially measuring lactate, and then the Opla one is measuring a bit more.
So the Flux One, which is the first product your team launched, it's worn on the upper arm like a HR, like a heart rate strap, and it gives a continuous lactate measurement. What surprised me is that it only costs $49. So 2 questions. How is it possible that it only costs $49? And the second question, how is it possible that it can last up to 10 years?
Yeah, it sounds almost too good to be true.
Yeah, exactly. It sounds almost too good to be true. Like $49 and it lasts 10 years and you wear it around your arm and it tells you a continuous lactate reading.
Yeah. So 2 things. The Flux One, it's an NFC chip. So it tells you the lactate when you scan it. And then you get a lactate reading. So after some time, the AI will learn about your lactate reading at a given intensity. Usually, we tell people to have a heart rate monitor as well.
Okay.
Because then you have another parameter for training intensity, right? You have another signal to couple. So you need kind of multiple signals for training intensity to kind of get the right one through a process called triangulation. So you use multiple signals and then you try to converge them to get the right training intensity. And the Flux One is just one of them. It measures sweat, and sweat is somehow related to metabolic load. So how hard the body is working. Because it doesn't have any batteries, it just uses the NFC coil from the mobile to power it. The only thing that kind of get this wear and tear is the microchip. That is why it lasts so long. On top of that, we covered the microchip with a thick layer of epoxy, so it's encapsulated. It's completely warm. There's no moving parts. There's nothing to break, and I think that's kind of the mantra of Athyx. Like, we want to create something that people will think this is just too good. This kind of technology doesn't exist. We just give them try it, see if it works, and then let us know. And then so far we had really good feedback on the products.
So basically, the Flux One, the premise is to create a very low barrier of entry for someone that wants to get into continuous lactate testing.
Not only lactate testing, but as well into the whole ecosystem of doing this Norwegian model of training.
Very quickly, if you want to try continuous lactate monitoring, get 10% off the Flux One or any Athyx product using the link below with code ELAB10. Now, let's get back to the conversation.
There's 2 things about the Athyx. One is, of course, the wearable, but the other thing is about how do you train correctly. And those 2 things are that they can be intertwined, but they also mutually exclusive. Like, you don't have to use Athyx wearables. I shouldn't say this from the sales team, but eventually, one way to actually do a lactate test is to just do the talking test. Like, that's a low. Yeah. Like, you just you can spell out a few sentences, then you're probably around threshold.
Push threshold.
Yeah, exactly. So we were just trying to give people a very fast and easy way to get started with things.
And your next product, which will be the flagship product, and that's the Obla Eye.
So that's going to be available in July, actually, and the price is still to be determined. The Obla One measures much more than Flux. So Flux measures sweat. This is what Obla One does as well, but it also measures lactate through lasers, and then it has a heart rate monitor, temperature, accelerometer, and then power output as well. So it's kind of different sensors consolidated into one device. And again, these sensors are there to give an estimate of the training intensity. With these sensors together, you get a really good measurement of where the training intensity and the training capacity for that day. This is for people who want to measure more than just heart rate. I think we'll probably add saturation measurement to the Obla One as well. So in this case, we now have 6 different sensors in the Obla One, and you're able to I think get very close to the right training intensity.
And because it balances all these different data points.
Yes, so it uses an algorithm we made called triangulation by proximity. So it's trying always to get real-time measurements and then gauge into where is the training capacity for that day.
You mentioned lasers. The Obla uses lasers. Could you clarify that point a bit for someone that is a bit concerned about the lasers?
Okay. It sounds extreme, but these are not the kind of lasers you see at laser pointers. Like it's actually the same laser as you see in the iPhones used for 3D facial recognition. So they call VXLs, and we use these lasers to measure lactate in blood. So they are kind of things you use every day, and you can look at it. It wouldn't burn your eyes or burn a hole through your arm or anything crazy like that.
Okay. So it's uninvasive.
Yes, definitely it is.
And you wear the Obla on your upper arm as well, like a heart rate strap.
Yeah. In the future, we might release a wrist-based one, but wearing it on the arm gives you the most precise measurements, for every sensor. In this case, lactate, heart rate, temperature, SpO2, accelerometer, all these things. Yeah.
I mean, it's quite known that wrist-based, like when you wear a Garmin or Coros or whatever watch brand Polar that you wear on your wrist, if you don't have a arm strap or a chest strap, that reading is never that accurate on your wrist. Is it fair to guess that with the Obla, you don't actually have to wear a heart rate strap anymore, and you can actually use that as your heart rate strap connected to your Garmin or connected to your Coros or Polar or whatever watch that you have?
Yeah, it has internal heart rate. The components we use for the heart rate is basically the same as you use in medical devices. It's really high grade. It's going to be different. I think people will be quite amazed by it.
And it can pair with a sports watch, and you can see the data in real time.
Yes, and also right now our app can pair with other devices to look at metrics in real time.
What devices can you pair with right now?
Devices with Bluetooth. We've paired it with Coros, heart rate monitor, Stride, Polar, heart rate monitors. So everyone with a Bluetooth device, it can basically pair with it.
And you call it Obla, which is OBLA. Is it fair to guess that that's the acronym for onset of blood lactate accumulation? Or why? How did you come out with the name Obla?
That's right. Onset of blood. You've been reading on scientific stuff, man. That's good.
Yeah, I was just doing my research and, pull up everything that I can about lactate, and it came up with onset of blood lactate accumulation. I'm like, oh, that's probably why they call it the Obla. And I have to ask that reason because Obla sounds like a very strange name, right? Compared to Flux. So when I saw that, I thought, okay, maybe that kind of corresponded to the name of the product. Okay. The Flux and the Obla. Who is the ideal end user for the Flux, and who is your ideal end user for the Obla?
Flux is a low barrier entry to the system, and that could be for people who are either using lactate meters, or they thought about lactate meters, but then they don't want to take finger pricks, or it's too expensive. So they kind of miss out on that signal. While the Opla One is more for the people who are really into the training stuff and want to measure everything, make sure it's as accurate and precise as possible. And we also have some cycling teams, sports clubs who's been contacting us and want to have a sample of the Opla One. So these are professional teams, and they want to have continuous measurement on the whole cycling team of 20, 30 people.
So the Opla is more for the elites and I guess your competitive age group athletes, your podium chasers, whereas the test kit is for someone that is just starting out, that wants to get another data point, just get introduced to lactate and understand what it does in their body or how their body produces lactate.
Yeah, and it also be kind of a eye opener for people who have been stuck at a certain training level, and then they want to improve themselves, but they've been trying everything in the books and it just doesn't work. And I think that the Flux One, the greatest thing about it is that it humbles you. Like it will tell you when it's too fast, so you have to slow down. Like,
okay.
It can also give you kind of this red, green, and orange days. So
okay.
On the days when you sweat a lot, it's hot outside, you have to be super careful about your training, because the risk of going over a threshold is marginal. It's really small.
As we start to land the plane, if someone listening to this starts to open themselves to the world of continuous lactate measurements, what is one idea from this conversation that you hope that they'll apply to their training moving forward?
So one thing is that always err on the safe side, regardless of whether you're using Flux or you're using Opla or whatever it is. If you're asking yourself whether it's too hard, it's probably too hard. And I think a lot of people, they train with a lot of mind over body because they want to prove how tough they are and how much pain they can sustain. But in the end, it's not pain Olympics. And you want to take that asymmetrical risk. Like how do I get alpha? The highest amount of performance with the least amount of effort.
Peter, my closing question for you. As a 1 hour, 14-minute half marathoner, a sports medicine practitioner, and a startup founder, what does endurance mean to you?
It means life. I think it's the foundation of all life. Okay. I think everything revolves around how endured human beings have been. I mean, if you look at the whole evolution, the way we evolved, the way we moved through the Rift Valley, the way we hunted, we were never the strongest, fastest, or best swimmers. Like, we only have our big brains that require a lot of carbohydrates and proteins, actually. And the only way to gather all those resources is to be flexible. Like, you have to mobilize yourself over larger areas and different terrains, eating different things. And that's why I think we have to bring back like a primal instinct. Like I said in the beginning, the default version of human beings is endurance. I've seen so many issues, challenges, problems, psychological, somatic, in people that could have been solved if we just worked out a little bit. I'm not talking elite level. I'm talking the bare minimum, like 40 minutes of physical activity that can be easily integrated in transportation through to your work, back and forth. That could solve so many things. That's why endurance is kind of the one thing that binds everything together. Like we talk about this physiology, everything in our biology is built for endurance. Like every single cell, every hormone, everything is just maximized for endurance. Because endurance, back in the days when we didn't have Uber or all these companies, it meant survival. Endurance equals survival. And everything in the human body is optimized for survival, nothing else.
Peter, thank you.